Hi there everyone, I am Mayur Gohil. In this video lecture we shall go through something known as Cayley-Hamilton theorem. It's very important in the linear algebra and it is useful in topic of eigenvalues and eigenvectors. So let us see what does Cayley-Hamilton theorem say. It says every square matrix A which is of order n satisfies its characteristic equation. Is the very simple statement but a very strong statement. So let us see how to solve problems related to Cayley-Hamilton theorem. This type of problems are generally asked in examinations. So they ask verify Cayley-Hamilton theorem for a given matrix A, and then you have to find the value of some expression given in the matrix. Okay, so this is the matrix value that we have to find. So let us see first how to verify Cayley-Hamilton theorem and then go about it. So the first step will be let Ax equals to lambda x where x is not equal to 0. This is a standard step. After that, determinant A minus lambda I is equals to 0. That means we have to find the characteristic equation. Now the characteristic equation of this matrix will be lambda square minus the trace. The trace of this is 1 plus 1, that is 2. So minus 2 lambda and plus the determinant. If you solve the determinant, that is minus 15. So minus 15 equals to 0. Okay, so this is the characteristic equation. Now, so what does it say is that every square matrix A satisfies its characteristic equation. Now we have to verify this statement. We have obtained the characteristic equation, and in order to verify Cayley-Hamilton theorem, we will have to verify that when we substitute lambda equal to A and we obtain this as the equation over here, that is a square minus 2a minus 15i is equals to 0. Now this 0 on the right hand side is a 0 matrix. Remember that. Okay, so we have to verify this equation here. That is what is meant by Cayley-Hamilton theorem. So when we verify, there is always an LHS and there is an RHS. So in our LHS over here, we have this equation a square minus 2a minus 15i. So that is, this is our LHS. Now further, when you substitute the values of a square, 2a and 15i and solve that further, you will obtain 0 matrix, that is your RHS. Hence LHS is equals to RHS, that is a square minus 2a minus 15i is equal to 0, and hence Cayley-Hamilton theorem is verified. So that's it, and it's very easy. You straight away get almost 3 or 4 marks for this kind of a problem. Okay, now further what you have to do is you have to find the expression for this matrix 2a cube minus a square minus. So how do we do that? Let us see. We have to find a suitable expression for this matrix. So let us see how to go about it. Now you already have the characteristic polynomial with you, and here just see this. This is our characteristic polynomial. Okay, so now you divide this expression to a cube minus a square minus 35a minus 44i by this expression of the characteristic polynomial. Okay, and then you perform the division, you will obtain this format. Okay, that is, this is dividend is equals to divisor times the quotient plus the remainder. But now by Cayley-Hamilton theorem, you already know that this expression a square minus 2a minus 15i is nothing but a 0 matrix. So right, so this entire expression this product becomes 0, and what you are left out is that this cubic expression is equal to a plus I. Okay, so finally, when you substitute the values of a and I, you get your answer for your 2a cube minus a square minus 35a minus 44i. It's very easy. You can easily understand it, and then we are done. So, and the entire problem is solved. So similarly, try to do this two problems on your own. This is a 3x3 matrix. You just have to do the same procedure again. You have to find its characteristic equation and then verify Cayley-Hamilton theorem, and then whatever expression you derive, divide it, perform the division for this big expression. You will obtain some quotient and a remainder, and then the same technique follows of Cayley-Hamilton theorem, and your answer will be obtained in the form of the remainder, and that's it. It's done. And similarly for this problem also. So try them on your own and do let me know your feedbacks. Thank you.